Support for Central Florida Public Media comes from the University of Central Florida, offering their Masters of Science in Data Analytics program. Designed to enhance skills in data analysis and machine learning, the new Artificial Intelligence track offers specialized courses to deepen understanding of AI technologies and their applications. More at ce.ucf.edu/data.
Detecting plastics on Earth and Mars rovers with a mind of their own. You're listening to Are We There Yet?, the radio show exploring space exploration. Hi, I'm Brendan Byrne. What if technology on the International Space Station could see plastic pollutants in our oceans? That's what scientists think might be possible thanks to EMIT, an instrument that studies dust and minerals on Earth. Recently, it was able to see plastics on land. So what could EMIT do in the future? We'll speak with EMIT's Kelly Lewis and NASA's Raissa Estrella about how a space-based instrument could help clean up our oceans. Then NASA's rovers on Mars have a team of scientists here on Earth to help with their mission to study the red planet. But sometimes these rovers don't need human help. They can perform some tasks on their own. We'll speak with NASA's David R. Thompson about how they are designed to think for themselves. That's ahead on Are We There Yet? Aboard the International Space Station lives an instrument that studies minerals and dust that impact the Earth's atmosphere. And that tech is starting to observe something else on our planet: plastics. The instrument is called EMIT, or Earth Surface Mineral Dust Source Investigation. But aside from studying dust and minerals, a recent paper found that EMIT instrument can also detect plastics. These findings raise important questions and possible future use cases, like could this technology help in other areas of Earth observation, like detecting plastic waste in our oceans? Here to talk more about EMIT and its capabilities is Kelly Lewis, EMIT Mission's Aquatic Applications Lead, and Raissa Estrella, an astrophysicist and astrobiologist at the NASA Jet Propulsion Laboratory in California. Raissa and Kelly, welcome to Are We There Yet?
Thank you for having us. Thank you.
Hey, so let's start. There's really cool things coming for EMIT, but I want to talk about what is this piece of hardware. Kelly, can I start with you?
EMIT is, or the Earth Surface Mineral Dust Source Investigation. It is an imaging spectrometer, and it's installed in the International Space Station. As sunlight interacts with different surfaces, when that light bounces back to an instrument or detector, it has a very specific spectral fingerprint, and those fingerprints trace back to not just like is it a rock or vegetation or water, but it actually can start to distill what types of rocks might be there, what types of vegetation and water conditions. And I think that's like really special because with EMIT, it was initially designed to map mineralogy of dust-forming regions of this planet, but that underlying technology can be further used to support other types of applications, which is really what Raissa dug into.
Let's talk a bit about that, Raissa. What are you able to take from these observations and apply them to kind of monitoring what's going on our planet?
What we demonstrated that we could use EMIT to detect plastics from space. So we used EMIT to measure the reflected light from the surface. With this reflected light, you can see fingerprints, right? Like lives, minerals, or even plastics. And that's what we're looking for, is looking for pollution from plastics, because we know that plastics is a big problem in our planet. By providing a way to monitor this poor plastic waste management that we have in our planet, EMIT offers a tool to combat this global plastic crisis, which is threatening our soil and ecosystem.
Kelly, was this EMIT's intended purpose, or is this something you found out it was able to do once it was in operation?
I think what's really cool about this is that it was designed for looking at arid regions with lots of dust, but it actually comes from a long history of imaging spectroscopy technology that goes back 30 plus years at JPL. So it kind of first started on airborne platforms on Earth, but we've actually scaled this type of technology to be even used for moon mineralogy mapper. So that went up in 2008 and provided the first mineralogy maps of the moon. And then there was a discovery on top of that that was able to show that this instrument could discover water molecules in polar regions of the moon. So it comes from that same family of imaging spectrometers and technology. And today, that's, I guess, instrument sibling is on Europa Clipper, the mapping imaging spectrometer for Europa. So MISE, and that's on its way. So this type of technology has been around for 30 plus years, but it's also been this really cool opportunity to look at, all right, so we've done it. We've looked at this planet. We've looked at the moon. It's on its way to Europa. So I think there's always kind of been this seed of wait, we can do more with this instrument. And that's why I think it sets up somebody like Haisa really well to say like, all right, let's push it in a new direction.
Haisa, your paper demonstrated that, this technology and this technique can discover plastics. What do you actually see when you're looking at the data? How do you know that it's plastic?
We know what is the plastic fingerprint that's imprinted in the light that we measure with EMIT. So we know exactly with which color of light plastic leaves that fingerprint. What is difficult is to distinguish what kind of plastic is that one. So we try to do that in our research, but there are many types of plastics that humans created, right? So it brings a puzzle of us scientists to detect, what kind of plastics are we detecting? And that also brings up this problematic that we have right now in our planet that, when we think of plastic, we normally think as one single material, but actually it's, different types of polymers with different chemicals integrated on it and also additives, which makes it also very difficult to recycle. And that's why, we need to monitor these plastics. Yeah, and that's what led us to do this research.
I would assume that there is not a global database of all the plastics that are being manufactured that are just given to scientists like yourself, right? You kind of have to discern this on your own, right?
Yeah, we have actually some libraries that
Okay.
tell us what are the patterns of the fingerprints of each type of plastics. So we kind of have an idea what to expect when we look into that measurement from EMIT. But still, some of these patterns of these fingerprints, they can overlap. So it can kind of become difficult to distinguish between them. But yes, there are efforts for, building up library of different plastic types that we can use to train our data and improve this measurement and the differentiation of plastics that we're measuring from space.
Kelly, it baffles me that something from space is able to see things like these mineral dusts and plastics as well. What is the benefit of using kind of an Earth sensing device to track these things as opposed to the sensors that are down here on the planet?
I think I kind of appreciate this when I think about when an instrument like this is designed, they're trying to think about what is more of the spatial resolution question of like, how valuable is like a pixel from space versus having people on the ground going about and covering, different areas of the planet to measure. And I think one of my favorite stats is that the spatial resolution at the size of the pixel, that detail you can see is about a 60 meter by 60 meter spatial resolution. So that's, think, 2 Olympic hockey rinks right next to each other. And when it's doing these passes from space, you're getting that size footprint of our planet. The ranges that the ISS covers up to 51 degrees, the south latitude. So you're getting these pixels all across the planet. ISS passes, I believe it's a 90-minute orbit across. So that means you're getting all of these really detailed look. I mean, that's a lot of information. And then if we think about something in the ground that's trying to get that scale of information, I mean, it requires a lot of resources, but I think it's from more my application side of thinking is like that's what's really special about instruments in space is that we have all these really hardworking people trying to make these maps on the ground. And if there's another point of view from space or bird's eye that can help determine where to best allocate resources, that becomes a really powerful resource for folks.
You're listening to Are We There Yet? I'm Brendan Byrne. We're speaking with Kelly Lewis, the EMIT Missions Aquatic Applications Lead, and Haisa Strela, an astrophysicist and astrobiologist at the Jet Propulsion Laboratory in California. We're talking about EMIT's purpose and how it can now detect plastics on land. It's hard to explain that via a podcast or radio show here, but we'll post some links of some of the maps that your team has published, and you can really see the scope of what this sensor is able to pick up. Kelly, I want to talk about what you and your team are hoping to do next with EMIT and actually look for these plastics in water. Is that the next place where this technology is going to?
I might actually pass this one off to Haisa. And I say that because I think one of the biggest findings she had is that we can start to look at plastics at the source.
Definitely detecting plastic debris in the ocean would be very interesting. And I think it's the next direction as well. I think we still should continue to monitor the land because most of the plastics that we have that end up in the ocean actually comes from the land, right? So it's interesting to keep monitor plastics on the land. Our study monitor just for 3 months of data. We have years of data from EMIT. So, the time scale that we can monitor plastics on the land can be expanded. detecting plastics in the ocean can be tricky because the seawater absorbs the infrared light, which is needed to see the plastics. So especially if the plastic is submerged in the ocean, that's going to be even harder, right? Basically, the water is muting the fingerprints that we need to see from plastics with the instruments from space. If we have a plastics that is very high concentration, for example, there is the Great Pacific Garbage Patch, which is a large area in the North Pacific Ocean where plastics and all the debris are accumulated due to ocean currents, then maybe the chance of detecting plastics might increase. So that's something we need to test in the future. We would need to check, if EMIT has the spatial coverage from that area, but we can also think about all the potential instruments. There are other instruments that are in space that also measure the reflected light from the surface of our planet. We have PACE, and hopefully in the future, we have other missions coming up as well. So there is a potential coming up that we have right now and also in the future to overcome these challenges of detecting plastics in the ocean.
Haisa, I'm going to ask you a wild question. You may not know the answer to this, but could technology like this be used to look at other planets, to look for things like plastic, and maybe that is a biosignature of another civilization? I know you study astrobiology. Could this be used in that field as well?
It definitely could, actually. So the physics is basically the same. We actually are planning a mission called the Habitable Worlds Observatory that's going to be look into other planets outside of our solar system, much distant from here. And we're going to look into the reflected light of these planets. So these planets have, they're orbiting other stars, and they're receiving the light of their stars and they're reflecting it. So the same principle that we're doing with our Earth here, looking at reflected light, we are going to be looking to all the planets. So when we look in the reflected light, we can look for these fingerprints of techno signatures like plastics. We can also look for biosignatures like oxygen or water. Methane can be also a biosignature. So we're going to be looking to all that. We hope for that this potential observatory is going to be launched in the 2040s. Yes, in the future, we might be doing the same.
It's very interesting and exciting, but also discouraging to think that we assume that an alien world would also pollute their oceans with plastic too, and that's how we will find them, right?
Yes, yeah. I hope they are not doing the same in our planet.
Kelly, I'm gonna bring it back home. I'm looking at some of the maps that have been released: global plastics detection, acid mine drainage, wastewater runoff. Something that our Florida listeners will know about: algal blooms. You're able to see all sorts of these different phenomena across the globe. What do you hope the ultimate goal is from these observations? How do you hope this work will impact us down here on Earth?
I think what's really special about being in a place like NASA, where we're thinking about observations, how do we make the best observations to support people making decisions about environmental problems in their own backyard, and also planning for the future. And I think that's when I think about missions like EMIT, especially, and its siblings on this planet, it's just like we can pair both discovery of really interesting things like spectral fingerprints that can only be tied to certain types of minerals or plastic signatures, but also having that type of observation. And having that type of observation kind of helps us make better decisions for how do we be better stewards of this planet. So I think that's the big goal, getting these types of observations into people's hands. I feel like you've seen some of these maps, they're pretty inspiring. And I think that kind of sets us up really well to start thinking about, all right, what do we do with this information?
Haisa, Kelly, thank you so much for joining us.
Thank you.
Thanks for having us.
That was Kelly Lewis, EMIT Missions Aquatic Applications Lead, and Haisa Estrella, an astrophysicist and astrobiologist at NASA's Jet Propulsion Laboratory in California. Still to come, how humans are teaching Martian rovers to think for themselves.
Most of the time, the rover's operating based on a script of commands that are sent, executing its plan as best it can.
A look at how the rovers on Mars can think autonomously. That's ahead on Are We There Yet?
Support for Central Florida Public Media comes from the University of Central Florida, offering their Masters of Science in Data Analytics program. Designed to enhance skills in data analysis and machine learning, the new Artificial Intelligence track offers specialized courses to deepen understanding of AI technologies and their applications. More at ce.ucf.edu/data.
You're listening to Are We There Yet? From Central Florida Public Media. I'm Brendan Byrne. NASA's lunar trailblazer is lost. It was set to map the moon and identify where and how water is stored beneath the surface. But the mission never got to the moon. We'll speak with Joe Palca, a reporter and former NPR science correspondent, about what we know about the mission and its failure. That's next week on Are We There Yet? But for now, we are heading to Mars. The Mars rovers are making decisions all over the red planet by themselves. While there is a team of humans on Earth helping the robots roam and observe the red planet, Curiosity and Perseverance have the ability to work autonomously. So, how do they do it? Well, Are We There Yet's intern, Orion Boone, brought that question to David R. Thompson, a senior research scientist at NASA's Jet Propulsion Laboratory. Here's that conversation now.
There's a super cool instrument used on the Mars rover Perseverance called PIXL, right? Planetary Instrument for X-ray Lithochemistry. It's a big word. It's a long name. Can you tell me in simple terms what this cool little machine does?
Yeah, PIXL is an awesome instrument. It's an X-ray fluorescence spectrometer. So basically what it does is it has a source of X-rays, and you put this instrument up against a rock. It bombards the rock with X-rays, and those excite atoms in the rock that give off X-rays in response. And you can read the X-rays that come off of the rock and look for the signature patterns of different elements in that sample and characterize the composition of the rock that way. And so PIXL is a little instrument that sits at the end of the rover arm. It's a small box that's mounted on some extensible rods that allow it to move around with 6 degrees of freedom. So it has a lot of motion. Even once the rover arm is placed next to a rock, PIXL can move around quite a bit. And it will do what we call a raster pattern. That is, it will move back and forth across the surface of the rock in a tiny little area, about the size of a postage stamp, collecting its X-ray fluorescence measurement at each spot. And that way you can build up an image of the elemental composition of a rock at basically centimeter scale. So it's a really exciting instrument that the scientists are using as part of the Perseverance mission to understand Mars's surface and history.
That is so cool, the size of a postage stamp. It seems pretty small. What can it do at that size? And you mentioned it was continuing Perseverance missions for looking for signs of life. What is PIXL specifically looking for?
Yeah, well, PIXL is all about understanding the composition at microscales. So the individual grains of a rock may have differing composition that let scientists infer something about how that rock was formed. And this is important for understanding questions, of course, of habitability of Mars environment. So if we're looking for places where life was likely to occur in historical Mars, then we want to understand the conditions under which those Mars rocks formed. And where the most interesting samples are to collect to return back to Earth for even further, deeper analysis. So that's really what PIXL is all about.
One of the most interesting elements about PIXL to me is that doesn't Perseverance kind of make these decisions autonomously? What's going on with that?
Yeah, so PIXL is it's interesting in the sense that it can acquire better quality data if you spend more time to make a measurement. If you sit there at a single spot for a long time and record a lot of X-rays, you can get very, very precise information about that specific spot. But of course, the mission has to keep moving, and there's not a lot of time for all of these measurements. And so this was really the need for a little bit of onboard autonomy on the instrument itself to make some smart time allocation decisions, to know whether a particular spot is worth lingering over, acquiring a little bit more data so that the scientists back on the ground get the best possible picture of that interesting feature, or whether it can kind of race along in its standard acquisition pattern. And this was where the whole idea of adaptive sampling was born. So adaptive sampling does exactly that. It analyzes the data as it's streaming in from the instrument and matches it against templates that the scientists have defined in advance that are of interest. These could be particular features that they're looking for: carbonates, zircons, spinels, rock types that are really interesting to their scientific investigation. And when it encounters one of those, then it will spend a little bit of extra time to collect that high fidelity data, so that we're absolutely certain that that's what it found.
Adaptive sampling is such an impressive technology. How has it been used in Perseverance?
Well, we turned it on about 4.5 years ago, and it's been used pretty much consistently ever since then. Whenever the Perseverance rover deploys Pixel on a target, adaptive sampling is part of that command. And yeah, it's been used on dozens of different scans over the course of the last 4.5 years.
Obviously, Mars is pretty far. I'm sure there's a communication delay. Why is it important for the rover to make these decisions autonomously rather than just a human hitting a button on the ground?
Yeah, you're absolutely right. So Mars is really far away from Earth. It takes minutes for our signals to get there and minutes to come back. But really, we may only get a couple of communication opportunities a day, or even maybe one a day during regular operations. So most of the time, the rover's operating based on a script of commands that are sent, executing its plan as best it can. And this means that we may not get a second chance to look at that particular feature. Even if we wanted to place the arm at that rock again to try and come back to a particular grain that we thought was interesting, it would be very difficult to hit that exact same millimeter location on the surface of the rock. And there might not be time in our really rigorous schedule plan in order to take that action. So really, it's really important to acquire that extra data when we're right at the location, already placed and ready to go, rather than spend an extra day of mission time trying to go back there.
Fantastic. You're listening to Are We There Yet from Central Florida Public Media. I'm Orion Boone. We're speaking with David R. Thompson, Senior Research Scientist at the Jet Propulsion Laboratory, talking about Mars rovers making decisions autonomously. Switching over to Curiosity, the other rover working on Mars right now, we started doing something similar a decade ago using this onboard software called Aegis, right? Autonomous exploration for gathering increased science, making some decisions on what to look for with its chem-cam. How does it do this, and why is it important?
Yeah, Aegis was really the first gig that I had when I came to the Jet Propulsion Laboratory. After I graduated, I came out here to work on AI for the Mars rovers. Aegis is a slightly different kind of science autonomy. And by science autonomy, I mean onboard science data analysis and response. And Aegis looks for interesting features in imagery that the rover collects. In the case of Curiosity, these are images, camera images, looking for rocks that match a certain template, again, that the scientists have defined in advance as particularly interesting. You can use that to direct the chem instrument at those targets of interest in order to acquire data from them. So this is a laser mounted on the rover that will vaporize bits of the rock to understand their composition. And this is the sort of thing that would be very, very difficult to plan in advance, because the rover may be traveling through terrain that scientists haven't seen before, executing its script dutifully between command cycles. And the rocks that it passes, we may never have a chance to see again. So this lets the rover be a little bit more adaptive, just a little bit of rudimentary decision making that can help the scientists get the best quality data at the end of the day.
Yeah, it's really interesting. And hasn't Perseverance used Aegis too? I remember reading it back in 2022. It found 2 rocks and decided to examine them. How did it pick these 2 rocks, and why?
Yeah, Perseverance. Well, so I should start by saying that there are others on the team that have done a lot more work on Aegis than I have. So Aegis isn't my personal specialty, and I haven't been following the particulars of its targeting. But typically, Aegis will be trained to look for, or configured rather, to look for specific kinds of rocks. They could be larger. They could have a certain intensity profile, meaning that they're brighter or darker than the material around them. So really simplistic distinctions that you or I could make looking at an image, but of course it's not easy to get a computer to make those same decisions automatically, and that's really where the artistry comes in.
I mean, this is a massive advancement in space technology, right, over this past decade. These rovers are making simple but very important decisions. How does this help scientists maybe take a little bit of stress off their back in getting this data, and how does it really build up the amount of data we can collect from these rovers' missions?
Yeah, the issue that we face with Mars, those long communication times and intervals where the spacecraft is completely autonomous, are really magnified as you go further out into the solar system. As we get to the outer planets or beyond, we're going to have even longer intervals between communications. during which the spacecraft is totally autonomous. And in those situations, I think it's really not the case that we're trying to put an artificial scientist on board, right, to make science decisions. All of the important decisions about how to interpret the data, what the science goals are for the mission or for even the day or the traverse, those are made on the ground by scientists that understand the full context of what they're seeing. However, that said, there are simple distinctions that the spacecraft can make on its own to adapt to the data as it's coming in, as it's finding new environments, discovering new features of interest, about where to collect data and what to prioritize sending back that can improve the science yield of the mission, playing to the best strengths of both the robot and the human scientists on the ground.
One last question for you, David. Where do you think space technology is headed, Mars or otherwise, in the future, maybe next decade or even beyond?
Yeah, I expect we'll see an increasing adoption of AI, and this is, of course, speculation, but I think it's informed speculation based on what we're seeing both in low Earth orbit and with NASA missions as well. There's increasing interest and appetite of putting a little bit more autonomy and science data understanding on board, and now we have computers that are more and more capable to execute those kinds of routines. Now, spaceflight computing tends to lag terrestrial commercial computers by a decade or more in terms of technology. The computer that you have in your phone is probably more powerful than the computer on board the Perseverance rover, just because the rover version has to be hardened against radiation. It has to go through all sorts of extensive testing. It's sort of a different market niche than the commercial devices that you or I are more familiar with. And that means that these computers have traditionally been slower and less capable than what we're using on the ground. But of course, technology advances all the time. And as we start seeing more powerful computers become routine in space flight and in deep space exploration, we're going to see an increasing adoption of AI in those situations. Again, never trying to replace the human decision making about what's scientifically useful or how to interpret the data, but making increasingly sophisticated decisions about how to respond to the minute-to-minute environment that the spacecraft finds itself in and get the best possible data back home.
Fascinating. I'm really looking forward to, seeing where all this AI and space technology goes. We've been talking to David R. Thompson, Senior Research Scientist at the Jet Propulsion Laboratory. David, thank you.
Thank you, Orion. It's been a pleasure.
That was Are We There Yet's intern Orion Boone speaking with David R. Thompson, Senior Research Scientist at NASA's Jet Propulsion Laboratory. That's going to do it for this week's show. If you're not already, be sure to subscribe to the show's podcast feed so you never miss an episode. Do that on Apple Podcasts, Spotify, or wherever you get your podcasts. Stay connected with the show. Be sure to follow us on social media. You can find us on Instagram and Facebook. We're at AWTYSpace. And if you got an idea for a future episode of the show, or you want to join us as a guest, well, reach out. We're at arewethereyet@cfpublic.org. Are We There Yet is a production of Central Florida Public Media. Our intern is Orion Boone. Our producer is Marion Summerall. Editorial guidance comes from LaToya Dennis. Support for Are We There Yet comes from our listeners. Until next week, I'm Brendan Byrne. Thanks for listening.